Here we've got another reaction rate problem, and it starts off with this liquid called tertiary butyl chloride. In fact, usually this is just called tert-butyl chloride, which you can makes it nice and short, but it really should be called 2-chloro-2-methyl-propane, which means that it's built on a propane. A propane's 3 carbons. 1, 2, 3. So you imagine a carbon here, a carbon here, and a carbon here, which you'd see appropriately on this diagram. Now, the 2-chloro means that on the second prop of this, 3 means prop, the second of this prop molecule, we've got a chlorine. So there's a chloro on carbon 2, and there's a methyl group, which is a CH3 on carbon 2 also. So we've got our propane, which is 3 carbons, and on the second carbon we've got a chloro, and on the second carbon we've got a methyl. That would be the logical name, but this is used so often that they use the short tert-butyl chloride thing, which is something that organic chemists have to deal with. And when you take organic, you'll have to realize that you've got to memorize a lot of little things. And here's a vial of it. It's a liquid. It's used in making other organic compounds. Now, the reaction occurs in 2 steps. They've got a slow step where this stuff disintegrates and makes a cation. And then that cation picks up the hydroxide to become the alcohol. Now, the slow step of the reaction is what determines the rate law expression. And the only reactant in it is the tert-butyl chloride. And so that's the only thing we've got to worry about. So even though the rate here is shown, rate is equal to the constant times the tert-butyl chloride, the hydroxide, and this third thing, none of the hydroxide and this third thing aren't involved in the reaction. So it's only this. And we would therefore say the hydroxide's irrelevant, raised to the 0 power, and the cation here is raised to the 3rd power, 0th power also. So the rate law is just the rate is equal just to a constant times the tert-butyl chloride concentration. Now, notice here we have a 0.3 tert-butyl, and the rate is 6 times 10 to the negative 5 molar per second. It's a slow reaction. Then when the tert-butyl is doubled, the rate doubles, and we don't have to worry about the hydroxide. And here we've got 0.6, and the hydroxide's irrelevant. So therefore, you can figure out that what the rate is going to be. It's not going to be all that difficult. Now, also, since you know that all you have to worry about is the concentration of the tert-butyl, and you're given the rate and the concentration of the tert-butyl, you can calculate K pretty quickly, and I'll get my calculator out. So I can take any one of the trials here to calculate K. So I know that the rate is equal, let's try the first trial, 6, and then I'm going to go second function E, negative 5, and then divide by the concentration of the tert-butyl, which divide by 0.3, and that'll give me the constant for this example. Now let me try this other rate and see what happens there. I'm going to take trial 2, and I'm going to take the 1.2, second entry E, and again, negative 4. In this case, I'm going to divide by the 0.6. And if this constant is really, really a constant, we should be getting that same value. Indeed we do. And we know what the constant is, and we know that if you have 0.6, we get this concentration, and if you get 0.3, we get this concentration. All right, that takes care of it. This is the slow step, the critical part that determines the rate law expression, and you can forget about the hydroxide on this one.